Good morning, students. Welcome back to the GATE class. So we'll continue with the previous class. Hope all have joined. So we'll start with today's class. In the last class, we discussed about applications of op-amp, some of the applications of op-amp. So till now, what we have discussed about analog circuits is we started with introduction of op-amp, the characteristics of op-amp, basic op-amp circuits like inverting and non-inverting amplifier, and then we went on with the applications of op-amp, right? And we have discussed summer, summing amplifier, differentiator, integrator, comparators, Schmitt trigger, differential amplifier, oscillators. So we have touched many applications of op-amp, that to both open loop and closed loop configurations. And today we are going to discuss problems in these topics. Whatever we have discussed in previous classes, there also we have done few problems to understand the concepts. Now we are going to concentrate only in problems. So gate problems related to basics of op-amp and applications of op-amp, right? So shall we start with the class? Yes, this is first problem where you can see that a circuit is given with op-amp and transistor and we are asked to find the output of this circuit. Right? We all know that in the previous classes itself I have told that whenever a circuit is given and they have asked to find out some parameter from the circuit, the first step is we need to identify what type of circuit is that. If we were able to compare the given circuit with some standard applications, then with the help of those expressions we can directly find the output. And if it is not a standard application what we know, if it is some new circuit, then in that case we need to apply KVL or KCL, try to write some loop equations or current equation, nodal equation, something, and we need to sort out the required thing. We need to calculate the required parameter. Okay. So in that case, now if you see this circuit, given circuit, so first step, as I said, try to identify what type of circuit is this. Can you identify what circuit is this? Have you come across the circuit? Of course, you can see that the input is given to the inverting terminal, non-inverting is grounded, you have a feedback, everything, right? But what is the difference here? We have not seen a circuit where you have a transistor in the feedback. Is it not? We have seen only capacitor in the feedback, resistors in the feedback, right? So here you have a transistor in the feedback. So we are not sure about what circuit is it, okay? So we can find out what is the output of the circuit by writing equations, okay? Uh, I'll give you the clue, I'll give you the logic. Try to find out what will be the answer for this. Options are given. You can see 4 options are given. If not, if no options were given, it is difficult to find. But options are given now. I'll give you the clue also. Try to find out which answer matches. Now, from where you have to start with this problem is, you can see that there is a transistor. Let me take the pointer. Yeah. There is a transistor in the feedback, and in this transistor, the base is grounded. Okay, the base of the transistor is grounded, emitter is connected to output, and collector is connected as a feedback to the inverting terminal, right? Now here only we are going to analyze. Now, whatever current that is generated here, it cannot enter into the op-amp. It has to take up this path only. But here, already base is grounded, and by the golden rule of op-amp, since non-inverting is grounded, this terminal will also be at ground potential. Okay, so this is grounded and this is also at ground potential, right? So it means this is also 0 and this is also 0. It means this junction is inactive. Okay, it is like a short circuit, it is inactive. This is also at 0 potential, this is also at 0 potential. So only valid junction is this one. Okay, this junction need to be forward biased. Only if this is forward biased, the current can flow through this path, is it not? Because you have a source here, you have a resistor, so your current will be generated here. And that current, as we know, it cannot enter into the op amp. After it starts from here, it has to flow through this path, right? So you should have a closed path here. Okay. So it means the current will be flowing through this transistor in the emitter base junction, right? So with this, try to find out what is the output. Okay. The output at this point, it is nothing but the emitter voltage of this transistor. So just if you find out the emitter voltage of the transistor, that is the output of the entire circuit. Very simple. You have to just think the logic. That is what you have to do here. Otherwise, the problem is simple. It doesn't require a big calculation and all. Okay. So just try to find out what will be the output. Very simple. You need not calculate anything here. You need not do calculations. Known concept. Yes. Anybody have got the point? What should be considered here? They have told that this junction is inactive. So what is the only active junction? Base emitter. What will be the base emitter voltage for any transistor? Will be for a silicon transistor they have given. So what is the base emitter voltage for a silicon transistor? Yes, zero point 0.7 volts. So 0.7 volts between base and emitter of this transistor. So VBE is equal to 0.7. So VB minus VE equal to 0.7 means then what is VE? The emitter voltage? It is minus 0.7 and emitter only is connected as the output here, and therefore your output is also minus 0.7 volts. So the correct answer for this problem is minus 0.7 volts. Getting it? See, this is what. See here, we have shown all the calculations regarding the current and all. Anyhow, we need not bother about how much of current is going to flow there and all, right? So anyway, how will you calculate the current that's coming from the source? We know that the source is 5 volts. Here the resistor is 1K. So the current that is flowing in this path will be V by R, which is 5 divided by 1K, and therefore it is 5 milliamps. So the 5 milliamps current that is started from this source, it cannot enter into the op amp, and therefore the entire current has to flow in this path. And since this is inactive, the same current flows here, and this current will be making this junction a forward bias junction. Okay, and therefore the voltage drop across this junction will be 0.7 volts. So that is what shown here, right? The current is 5 milliamps and the collector current is at virtual ground, base is already grounded, so collector current is 5 milliamps. So this makes the base emitter junction as 0.7 volts, and finally the output will be minus 0.7 volts. Okay, clear? Shall we move to the next problem? So this is very simple, right? We'll move to the next one. Yes, now take up this circuit. Here again, we have been asked to find what is the output of the circuit. Okay, the question is just to find the output of the circuit. All the parameters have been given. How will you find the output of the circuit? First thing, as I said, you have to check whether the given circuit is a known standard circuit. Just see, if I take this op amp, the first op amp, I could see an input given to the inverting terminal and input given to the non-inverting terminal. We know, how will we check? Whenever an input is given to the inverting terminal alone, we have to check whether it is an inverting amplifier. When an input is given only to the non-inverting terminal, then we have to check whether it is a non-inverting amplifier. When input is given to both inverting and non-inverting amplifier, then we have to check whether it is a differential amplifier, and if all the resistors are equal, it can act as a subtractor also. So that we have to check, right? And apart from resistor, if you have any other capacitors in the circuit, then we have to see whether the capacitor is in the feedback path or it is in the input side. If it is in the feedback path, we can identify it as an integrator. If it is in the input side, we can identify it as a differentiator. Okay, when there is no feedback, it comes under the category of comparator. If there is a positive feedback, then we can identify that to be a Schmitt trigger. Okay, so this is how you have to identify the circuits, right? So by seeing this, I could see that two inputs are given in two different terminals. So I need to check whether it can act as a differential amplifier or subtractor. When I compare this circuit with that of a differential amplifier circuit, I don't think it exactly matches. Of course, you have an input given here and you have an input given to the non-inverting terminal, but you should have a resistor to ground here. Okay, that part is not available. Of course, you have the feedback part. So since we cannot directly use the equation of a differential amplifier, what we have already seen in the previous class, we need to write KVL equation, KVL or KCL equation, we'll see. Okay, KCL equation, probably mostly we'll be writing the nodal equations only. Okay, so write KCL equation for this and we need to find out. Similarly, see the second part of the circuit. Is this a known circuit? Here input is given to the non-inverting terminal, you have a feedback, and the inverting from the inverting terminal you have one resistor to ground. Okay, so first identify what circuit is this. Okay, and try to write equations for this. Just think for a while from where you can start, how to find. Okay, then I'll tell you what you are supposed to do. Just take a minute time to find out how to proceed with this. Second half of the circuit is a non-inverting amplifier. Hope you can identify that. It's a non-inverting amplifier, right? So start from the known one. This is a non-inverting amplifier and this we don't know, right? So since we know this, here I know the resistor values. Okay, I am not sure about what is the input and what is the output, but I can find the relation between input and output. Is it not? Output is equal to 1 plus Rf by R1 times the input. Rf is 1 kilo ohm, R1 is also 1 kilo ohm. So 1 plus 1 by 1, that is 1 plus 1, 2. 2 times the input. So output is equal to 2 times the input, right? So that we have got. V out is equal to 2 times this input. Let us take this point as some variable like VA. So V out will be 2 times VA. Okay, so we have known this. We know this now. So once you find out what is VA here, I can find out what is V out, right? So how to find VA? We have to write KCL equation. You want to write equation including this VA. So let me check out here. Here I have a node. So if I try to write the nodal equation for this, I know what is the voltage here, resistor here. Similarly, this side, this is known and this is the only unknown. And the voltage at this point, what will be the voltage at this point? If that is also known, then everything else is known except this VA. Is it not? So you can find out, you can write KCL equation for this node and you can find out what is the output at this point, right? So for that first step, you should know what is the voltage at this point. For that, you need to apply the golden rule of op-amp. Whatever is the voltage at one terminal, the same voltage will exist in the other terminal also. So if you see the non-inverting terminal, here 1 volt is given, 1 kilo ohm resistor is here and it's directly connected to the non-inverting terminal. So what will be the potential at this point? Can anyone guess? Potential at the non-inverting terminal, this point. No, you need not know about the current. Of course, current, yeah, okay. If you know the current, I can say from 1 volt, based on the current, I can find out what is the drop across this resistor and the remaining is available here. But that is not required. Why? I say that the potential at non-inverting terminal is same 1 volts as you have here. whatever you have given here. That means there is no drop across this 1 kilo ohm resistor. Why? Why? Because there is no current flowing in this path. Why there is no current flowing in this path? Because we know that no current can enter into the op amp. The other golden rule of op amp, no current will enter into the op amp. So it means if a current start flowing from here, it should have a path, is it not, to complete it? Only if there is a closed path, there will be a flow of current. But here, no current will enter into the op amp because of high input impedance. It is like an open circuit here, and therefore the voltage what is applied here, it will not flow into this. Okay, I mean the current will not flow into this, and therefore the entire voltage will be available at this point. Okay, the entire voltage will be available here, the same 1 volt. So this is 1 volt. Okay, since this point is 1 volt, this point is also 1 volt. Getting it? So now everything is known. The voltage at this position is known, this is known, the resistors are known. So try to write KCL equation for this node and find out what is VA. Once VA is found, 2 times of that will be V out. Yes? Completed. I've given the complete logic for this. Only thing is you need to work out and get me the answer. Make it, try to find out the answer. I'll give you time. 2 minutes. Try to find out what is the output. Yes, hope you people are doing. Find out what is the output of the first op amp, and then you can proceed with the output of second op amp. Sorry. Got it? Anyone can give the answer? Yes, can anyone give the answer? Still doing? Make it fast. Yes, someone is giving the answer. Yes, 8 volts. 8 volts. Fine, good. I'm showing it. See? First step, you need to calculate the voltage of output of the first one, the output of the first op amp. Okay. The output of first op amp, if you write equation for this part, this voltage, okay, they have taken this as second op amp. This is 1 volt is given here, means the same 1 volt will be available here, which is designated as V2, and therefore the same thing as V2 here also. So it means how will you write the equation now? This voltage is taken as V1. Okay, so with V2 as the node, okay, V2 minus 2 plus V2 minus V1, everything both divided by 1K. Okay, that is, if I write KCL equation for this node, it is V2 minus 2 volts divided by 1 kilo ohms plus V2 minus V1 divided by 1 kilo ohms is equal to 0. Total current in this node will be equal to 0, where V2 will be equal to 1 volt. So substituting that and rearranging, you are getting V1 to be 4. So that is this voltage to be 4 volts. If this is 4, since it is a non-inverting amplifier, you can say output is 1 plus Rf by R1 times the input. Input is 4 volts. 1 plus Rf by R1. 1 by 1. So 1 plus 1 by 1 is 2. 2 into 4, your final output becomes 8. Clear? Understood? What is the output? How you got the output for this as 8 volts? Yes, any doubt? Okay. We'll move to the next one. Third problem. Now this is very, very simple. Try to find the output of this. Okay. I am not going to tell you anything for this one. Make a try. Try to find the output of this circuit. Again, of course, this is not a standard circuit. You could see input is given to the inverting terminal, non-inverting grounded. You have a feedback, but along with the feedback, you have one more resistor also here, which is grounded. Okay. So it's not a usual inverting amplifier circuit, but still, anyhow, try it and see what is the output you are getting. They are not asking the output, the voltage gain of the amplifier. It means output by input. V naught by Vn. You have to find out V naught by Vi. Okay, so how will you do? When nothing is known in a circuit, always we have to write some equations to find it. Okay, so try to write a equation for this. Consider the inverting terminal. Okay, consider this point. Since non-inverting terminal is grounded, inverting terminal will also be at ground potential. With this as reference, a referral node, write nodal equation for this referral node. Okay, this side you have which is connected to Vi, this side it is connected to V naught. Write a nodal equation for this. Just simplify, you'll get the output. Very simple. They're not asking output V naught by Vi. Yes. Shall I show the equations? See, I have tried nodal equation at this point. Can you try what will be the equation if I take the voltage at this point to be V? V minus Vi by R1, V minus V naught by R2 is equal to 0, where V is equal to 0 volts. Substitute and see. So V naught by Va will be equal to say minus R2 by R1, that is inverting amplifier gain. So though the circuit doesn't look like an inverting amplifier, but still the gain of this circuit is also minus R2 by R1. Okay, the R3 is ineffective because from this it has been grounded from this point. Okay, it will not have an impact on the output. The output depends on only R1 and R2 as an inverting amplifier. Okay, understood? So the answer is minus R2 by R1. That is option A. Option A is the answer, minus R2 by R1. Clear? Okay, shall we move to the next problem? A Schmitt trigger problem. Consider a Schmitt trigger, a triangular wave. We are applying a triangular wave to this Schmitt trigger from minus, which is varying from minus 12 volts to plus 12 volts. And the output we are assuming to swing between plus or minus 15 volts, because for a Schmitt trigger, for comparators and all, output will be only between the saturation levels, is it not? Plus Vsat to minus Vsat. So here they have given what is the saturation level. It will be plus 15 and minus 15. So output swings between plus 15 and minus 15. Okay. And what else is given? Input is swinging between minus 12 and plus 12, and it's a triangular wave. Now we have to find out what will be the voltage swing at the non-inverting terminal, because we know that in a skimmer trigger, whenever the output changes, the reference voltage which is fed back to the non-inverting terminal will also change, is it not? So output is swinging between plus 15 and minus 15 means what will be the change in the reference voltage which is there at the non-inverting terminal of the op amp? That is the question. Understood? What is given and what is asked? A schematic circuit is given. They have given us what is the input value. It's a triangular wave between plus or minus 12 volts. Output is swinging between plus or minus 15 volts. And the question is we need to find the reference voltage which will be there at the non-inverting terminal of the op amp. Yes? So how to find that? How will you find? Of course, we know this is a schematic trigger circuit, but still it is connected to this plus or minus 15 volts through a 10K resistor like this. Okay, so this part we didn't see in the general schematic trigger. Okay, even now this will act as a schematic trigger only, but here you cannot directly write equations what we have obtained in the normal schematic trigger. Okay, an inverting schematic trigger what we have seen in the class. Okay, so better you can go on with the writing the nodal equations for this circuit also, but you should know which equation you should write to find out what is asked. You have to find the voltage at the non-inverting terminal, so write a nodal equation at the non-inverting terminal itself. That is, this is your node. Now with this as node, write a nodal equation. So you'll have a current in this path, you have a current in this path, and you'll have a current in this path. So total I1 plus I2 plus I3 will be equal to 0. See here, this side it is connected to minus 15, and here this is connected to, so both has been given as minus 15. You can take one as plus 15. Either take this as plus 15 or this as plus 15. That doesn't matter because anyway both the resistor values are equal, is it not? This is also 10K and this is also 10K. So instead of minus 15, minus 15, see we have applied supply voltage, we have given supply voltage to the op amp. Okay, so it means it should be plus 15 one place and the minus 15 in another place. Okay, so it is shown wrongly here. So take one of the voltages plus 15 and the other voltage is minus 15. Write the nodal equation for the non-inverting terminal and it will involve V naught also. So then find out what will be the reference voltage what you have here. If you take the voltage at this point as V, try to find out what is V. Okay, I have given the clue, right? So with that, try to work out and find out what will be the voltage swing at non-inverting terminal. Find it out. Yes. Hope you all are doing this problem. Schema trigger what we saw in the last class. So based on that, you have to find out the reference voltage. We'll know that in a schema trigger, you will not have a constant reference voltage. Based on the change in the transition in the output voltage, you'll be having a transition here. Yes. Let me show the answer. Anyone? Anyone have got the answer? See, suppose if this minus 15 is not given, We need not do the problem. Directly we can say what will be the reference voltage here. Because in the circuit what we discussed, from V0 you'll have two resistors like this, and here it will be grounded. Okay, so no potential will be applied here. So if this is grounded, okay, then I can say whatever is my output, it is divided equally among the resistors, because this is also 10K and this is also 10K. So half of that will be fed back here. So if this is the output they have given, plus or minus 15 volts, is it not? So it means plus or minus 7.5 volts will go here. So this is the case when this part is grounded. Okay, so that option is also available, plus or minus 7.5 volts. You should not get confused here. Okay, if you directly apply the equations what we have seen in schematic, then it will result in plus or minus 7.5 volts. But here if you see this side, the resistor is not connected to ground potential. It has been connected to minus 15 volts, the biasing what is given to the op amp, right? And similarly, you have a resistor connected to plus 15 volts here in the inverting terminal also. So these are the changes we have here in the symmetrical circuit, and since then we are not using the direct logic to find out the voltage at non-inverting terminal. Okay. And your answer is actually plus or minus 5 volts. Just if you write the nodal equation, hope you are getting it. Yes, 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 yes. Plus or minus 5 volt. Just write the nodal equation at the non-inverting terminal, rearrange, you will get it as V1, that is the potential at the non-inverting terminal, is V0 by 3. But what is V0 given in the question? Plus or minus 15 volts. So divided by 3, it will come as plus or minus, it will come to plus or minus 5 volts. Okay. So the final answer for this problem is plus or minus 5 volts. This, which is option C. The output swings between plus or minus 15 volts, then the reference voltage will swing between plus or minus 5 volts. You can draw the output waveform also. Okay, you can draw a waveform for this. Why don't you make a try? You have to draw input and output. Input is a triangular wave, okay, between plus or minus 12 volts. This is plus 12 volts, and this is minus 12 volts. It's not us, but we should, if you have understood the concept, you can draw the waveform also. Okay, so this is input, and now we have found it to be the reference voltage to be plus or minus 5, is it not? Let me take this as 5 volts, and somewhere here as minus 5 volts. Okay, this is plus 5 and this is minus 5 volts. So how will you draw the output waveform for this? When your input is less than 5 volts, reference voltage is 5, is it not? So when your input is, the input what you have given here, when this input is less than 5 volts, it means 5 volts only is greater, right? So your output will be at plus 15 volts. So your output will be at plus 15 volts till this. Okay, this is 15 volts, right? And once your input crosses this 5 volts, what will happen? Your output, your inverting terminal input is higher, and therefore your output will go to minus Vsat. So at this point, your output will go to minus Vsat. Where is my pen? Yes. At this point, it will go to minus Vsat. Okay. And your reference voltage changes to minus 5 volts now. So when your input is compared with minus 5 volts, this input only is always greater, and therefore it will remain in this minus 5 volts itself. Again, where I have left my pen? I couldn't find. It is here. right? So minus 5 volts till this, and once your input is lesser than minus 5 volts, your output again switches to plus V saturation. Like this will go on. Okay, so this is the input and output waveform between plus or minus 15 volts, and you have a triangular waveform in plus or minus 12 volts. Getting it? Understood? This is what we did in the example, what we saw in last class, right? Able to get the waveform? I have drawn the input waveform between plus or minus 12 volts, and we have found out in this problem that plus or minus 5 volts is the reference voltage. Whenever your input is less than 5 volts, your output will be at plus Vsat. Whenever your input is greater than minus 5 volts, then your output is at minus V saturation. In between all the stages, it will remain in the previous state, right? So between plus 5 and minus 5 is the hysteresis. Will not have any change. Lesser than 5 and sorry, lesser than minus 5 and greater than 5. In both the cases, it remains in the same state, hysteresis loop. Okay, fine. So we'll move on to the next problem. This is a easy problem. Again, and circuit is given, you need to find the output of the circuit. Now, I'm not going to give any clues for doing this because it's a very simple problem where input is applied to both the terminals of the op-amp. It looks actually like a differential amplifier. You can solve it like a differential amplifier, but for a differential amplifier, I'll give you this, I'll tell you this alone. For a differential amplifier, these two resistors should be equal, and this resistor and this resistor value should be equal. Okay, if that is equal, directly I can write output is equal to R2 by R1 into V1 minus V2. Okay, but here these two resistors are different. This is equal, these two are different. So it means you have to work out either by superposition theorem or by the golden rule of op-amp. You can solve this in many ways. Consider one input at a time. You can say that one input is applied to the inverting terminal, one is to the non-inverting terminal. You can take this as V1, V2. Consider V1 alone, find out the output. Consider V2 alone, find the output. Then you have to sum it up. This is using superposition theorem. Or you can find out what is the potential at this point, what is the potential at this point, and by the golden rule of op-amp, you can say this is equal to this, and you can find out the output. Or you can write nodal equation in any of these places. Okay, write nodal equation for this point, and you can find out what is the output. Anything you can do. So I have given all the methods. All the methods are simple. So try to solve this and get the answer for this one. Yes, use any one of the method, whatever I've told now. Any method, try to find the answer for this. Yes. Resistor values are very simple, no? And input is also very simple, 1 volt. So easily you can get the answer for this. Use any method, whichever I've told you now, whichever you're comfortable, try to find out the output. Okay. Answer is minus 0.5 volt. Answer is minus 0.5. Getting it? So here one of the method is shown. Okay, you need not solve the problem in the same way as it is shown here. That's what I said. You have different ways of solving a single problem. Okay, you can use any method. You can use nodal equation to find out. You can use superposition theorem to find out. You can use the golden rule of op-amp to find out. You can use anything here. They have I think here they have taken the golden rule of op-amp to find it out. V plus is found and V plus and V minus are same. With that logic, they have written the current equation and they have found out what is the value. But your final answer, it is minus zero point 0.5 volts. Getting it? It is minus zero point 0.5 volts. Hope you are getting this right. Now next one, next problem, we'll move on to the next problem. Can you see the problem? The voltage E naught is indicated in the figure has been measured by an ideal voltmeter. That is the output of the circuit. Which of the following can be calculated? If you know these things, that is, two resistors are there, you can find out the value of that, and output is also known. Consider that output is also known. E naught you are measuring with a voltmeter. Then what are the things you can identify from this? Bias current of the inverting input. See, this is based on non-ideal DC characteristics. Okay, you have DC characteristics of op-amp, AC characteristics of op-amp. This bias current and all, it is DC characteristics of op-amp, non-ideal DC characteristics. Okay, you have bias current, offset voltage, offset current. Okay, so all these things are non-ideal DC characteristics. Okay, so now with for the given circuit, you should say that whether it is possible to calculate only the bias current of the inverting input, or the bias current of the inverting and non-inverting input, or input offset current, or both bias current and input offset current. Bias current means the current that is entering into the op amp. See, ideally speaking, no current should enter into the op amp. We'll consider that as the golden rule of the op amp. So ideally speaking, current entering into the op amp is zero. But practically speaking, a very small amount of current will enter into the op amp. Okay, that small amount of current only we call it as the bias current. And the current that is entering through the inverting terminal is called as inverting bias current, and the one in non-inverting is non-inverting bias current, IB minus and IB plus. That is what we use. Okay, so whether you will be able to calculate the bias current at the inverting, bias current at the non-inverting, or both the bias currents, okay, or input offset current. Input offset current means the difference between the bias current. As we said no, IB minus, IB plus are the bias currents. The difference between the bias current, IB minus minus IB plus, or IB plus minus IB minus, something. We are not bothered about the polarity. The difference between the bias currents. Okay, if you are able to find that, that is what we call it as offset current. Okay, so whether you will be able to find that offset current from this, or both bias current, offset current, everything can be found out from this circuit. Just see. Circuit is very simple, no? Just think and tell me whether you will be able to find one parameter or both the parameters. Check it out. Just try to see what you can do with the circuit is very simple, no? You cannot write bigger equations and all here. Just try to identify what equation you can write here, and with that equation, what could be found, whether bias current or offset current or both. Yes, able to get it? So we'll try to write equation. How will you start doing this? Let us assume the current here in non-inverting terminal as I plus, and the current here in the inverting terminal as I minus. The voltage here as V plus and the voltage here as V minus. Okay. So try to write equation for the current that is flowing in this, that is I minus, and the current that is flowing here as I plus. Try to write both the equations. From that, find out what is V plus and V minus. Equate those two because we know that both will be equal. So V plus equal to V minus, equate it and see what is that expression you are getting. From that expression, you can identify what option is correct here. Okay, I've given the procedure now because you will, I hope everyone is confusing from where we have to start for this, right? So I've given you the steps. Try to write equation for the current here in this feedback. Try to write the equation for the current here, which is I plus. And then find out V minus, find out V plus. By golden rule, V minus will be equal to V plus. Equate and try to get the expression. I hope now you can do it. Yes? Try it out. See? We have taken the current I minus, which is flowing in the inverting terminal, that is inverting bias current. Okay, so that will be equal to the current here is the voltage on both the ends divided by the resistor. So E naught here and V minus here. So E naught minus V minus divided by 1 mega ohm. Similarly, this will be 0 minus V plus divided by 1 mega ohm. This is I plus, this is I minus, and this is I plus. Okay. From this, you identify V minus. From this, you identify V plus. Equate both, since for an ideal op amp, V minus is equal to V plus. You equate both. You will be getting an expression as E naught is equal to I minus minus I plus into 1 mega ohm. This 1 mega ohm resistor, okay? I minus into 1 mega ohm minus I plus into 1 mega ohm. So it is I minus minus I plus into 1 mega ohm, right? So the difference I said, no, the difference between the bias current is nothing but the offset current. So I minus minus I plus can be written as the offset current IOS. Okay, so IOS into 1 mega ohm. So what you can found from the given one, I could able to find what is IOS. That is the offset current. But will you be able to find IB minus and IB plus? No, because E naught is equal to IOS into 1 mega ohm. From this, I can rearrange IOS is equal to E naught divided by 1 mega ohm. We said no, E naught will be measuring with a voltmeter. So whatever value it is showing divided by 1 mega ohm will be IOS. But what about I minus and I plus? Is it possible to find out what is I minus and I plus? No, right? Because I minus equation, if you see, E naught we know, of course, we are measuring, minus V minus, we should know what is the potential at this point. Only after measuring the potential at this point, we'll be able to say what is the current I minus. Okay. This, we know that this potential is equal to this potential, but we are not sure about how much is the potential. Okay. So you cannot measure the bias current using the given data. Okay, so because V minus is required for it. So which option is right? We can measure only offset current. See third option. Because bias current and inverting input not possible because you require V minus. Bias current both inverting and non-inverting not at all possible. Input offset current. So that is what possible just now we saw. Both bias current and input, that is not possible, right? Okay. We'll move on to this very easy problem where we have been asked to find out the CMRR value, common mode rejection ratio. Is it not? We all know CMRR is equal to AD by AC, differential gain by common gain. Okay, everything is given in the question. Can you find out the answer for this? Everybody tend to do it as AD by AC. AD is 48, AC is 2. 48 divided by 2, the answer should be 24, no? But the 24 option is not here, no? Is the problem wrong? Have they forgot to give the option? No, right? So what must be the answer? Something given here, it must be the answer for the given question, right? So how to do this? Very simple problem, but still we are not able to get the answer. AD by AC, when I put, you'll not be able to see what is the output for it, right? So what is the trick here is, see, you can see that differential gain and common mode gain both are given in dB, not the simple values. It is not given as simply 48 and 2. If it was given like that, then the answer will be 48 divided by 2. You can directly write it as 24. But you should notice here that both the values are given in dB. Okay, so if it is in dB, then what is that? 20 log CMRR will be equal to 20 log AD by 20 log AC. Okay, so in log 20 log AD by AC. So in log different division is equivalent to subtraction. Is it not? Log A by B can be written as log A minus log B. So you should do this problem as 20 log 48 minus 20 log 2. Okay, it is actually 20 log of 48 minus 2. So it comes as 46 dB. Okay, so the answer for this problem will be 46 dB. Differential voltage gain and common mode voltage gain both are 48 and 2. You should not divide this. You are supposed to subtract because it is in logarithmic scale. Okay, see, simply CMRR is AD by AC, but we are calculating here as 20 log CMRR, which is equal to 20 log AD minus 20 log AC. This value is equal to 48 and this is equal to 2. So it comes to 46 dB. Is that clear? So which option is right? Option C is correct answer for this problem. Okay, now next problem. Try to do this one. If the op amp is an ideal op amp, we have to find out what is the output voltage. Again, it looks like a differential amplifier as we saw in the previous problem. It looks like a differential amplifier because two inputs are given in different terminals of the op amp, one to the inverting terminal and the other to the non-inverting terminal. You have a feedback resistor and you have a resistor to ground also. But you cannot directly use the differential amplifier formula here because this resistor value what you have in the feedback and this should be equal, is it not? Then only we can use the differential amplifier formula directly here. But here these two resistors are equal, but this feedback resistor and this ground resistor, they are not equal. One is 5K and the other one is 8K. So since you have two different values, we have to write nodal equation for this and you have to find the output. You cannot directly use any formulas what we have seen already. Okay. So again, this problem you can solve it in many ways. You can either go with the superposition theorem, consider one input at a time. Two inputs are here. No, consider this input, inverting input, ground the non-inverting input, find the output. Similarly, consider non-inverting input, ground the inverting input and find the output. Then sum up both the outputs. That will be problem solving based on superposition principle. Or you can write the nodal equations. Write KCL equation for this node, write KCL equation for this node. Okay, and then comparing these two, you can find out what is the by op amp. Both the values should be equal, is it not? The potential at the inverting and non-inverting should be same. So using that, you can find out. Or directly, you can apply the golden rules of op amp. Okay, you can write the KCL equation for this alone, for this part alone, and then you can find out what is the output of this. So somehow use any method. Okay, whatever may be the method, that doesn't matter. You have to finally find out the output of this given circuit. So use any method and try to find the output for this. Similar to the one what we saw 2-3 problems back. So try to solve it. Use any method. Either you go by superposition principle or the golden rule of op amp. Anything is okay. Try to write the equation, substitute the values, simplify and give me the final answer. You have four options here, 1, 6, 14, and 17. So work out, check which answer you're getting. Once you have finished, you can give the answer for this. Yes, hope you people are doing it. Okay, I'm showing the output for this. It is 6 volts actually. What you have to do here, one of the method it is shown here. Again, I said you need not follow up with this one. Use any method. Okay, here they have found what is the potential at this point, what is the potential at this point, and then both are compared. Okay, so here the voltage at this point you can calculate using a voltage divider rule. 2 volts is given, 1 and 8. So it is actually here, I forgot to tell you, not have got the 6 volts because there's a mistake in this problem. Here they have interchanged the values. Actually, the potential at inverting terminal is 2 volts and potential at non-inverting terminal is 3 volts. Sorry, I forgot to tell, interchange this. Just before the start of the class, I noticed this. This is 2 and 3, you should interchange. Then only you'll be able to get 6. Or else solve with this 3 and 2 itself and find out what is the answer. Nothing wrong. You can find out the answer with that also. Yes? Getting this answer? Interchange 3 and 2 and give the answer for this. You'll be getting 6 volts, right? So this is how you have to solve problems whenever it is given. You always have a logic in solving the problem. First, you have to identify the circuit, then you have to find right equations, and then you have to solve it and get the answer for this. Okay. Okay, time up. We'll wind up here. One more, the last problem. With this, we'll wind up the last one. 741 op-amp has a gain bandwidth product of 1 megahertz. A non-inverting amplifier using this op-amp and having a voltage gain of 20 dB. So what is given? 741 op-amp is given. Gain bandwidth product is 1 megahertz. Voltage gain is 20 dB. So bandwidth is asked. So what do you have to do? Gain into bandwidth is 1 megahertz. Now you have to find out what is bandwidth. So gain should be known factor. For gain, they have given it in dB. Gain value in dB is 20 dB. So remove dB and get the normal value of the gain. Substitute that here. Okay, so that value here, that into bandwidth is equal to 1 megahertz means both are known. So only unknown will be bandwidth. From that, find out what is bandwidth. Understood? It is gain into bandwidth. Gain into bandwidth will be equal to 1 megahertz. Okay. Here we know what is gain, but it is not directly given, it is in dB. Convert this into normal factor, substitute here. So you know this value 1 megahertz and this gain is also known. So only unknown will be bandwidth. From that you can find out what is the bandwidth value. Check it out, what will be the answer for this? The last problem, finish it off. Right? Yes, the answer is 100 kilohertz exactly. So first we are converting the logger value 20 log x into a normal value. 20 log x is equal to 20 means log x will be equal to 20 by 20, which will be 1. So log x is 1 means x will be equal to 10. Okay. So substitute that here. 10 power 6 divided by 10, you'll get 10 power 5, which can be written as 100 kilohertz. Okay. So this is the answer for this problem. 100 kilohertz. Okay. Okay, then we'll wind up the class.